When a polynomial is presented as a product of k distinct binary forms, the mathematical operation inherently loses information. The most immediate consequence of this multiplication is the intrinsic destruction of relative scaling directions. If you multiply one factor by a specific number and compensate by dividing another factor by that exact same number, the final product remains completely unchanged, meaning k-1 scaling directions vanish from the output. We can quantify this loss by looking at the geometry. The source space of the independent factors possesses k-1 more dimensions than the target space of the multiplied product. To fully understand the polynomial product, it is a mathematical necessity to isolate and recover these missing directions. The candidate paper addresses this gap by proposing an affine all-factor determinant line theorem. Earlier work on the two-factor case relied on a single-degree difference to measure this missing scale. This new theorem upgrades that simple rank 1 metric into a complete character lattice invariant capable of handling any number of factors. The proof is built across a strict three-layered architecture. It starts with differential geometry, moves into exact integer arithmetic, and resolves in global geometry. Mathematically recovering these lost scaling dimensions provides the mandatory foundation required to quantify the exact residual finite group ambiguity that remains in any polynomial factorization. The analysis begins on the pairwise coprime locus by examining the Jacobian matrix of polynomial multiplication. This equation shows the proposed affine all-factor theorem. It maps coordinates where multiplication loses more rank than relative scaling alone explains. Looking at the right side, the first half isolates delta D, defined as the product of all pairwise resultants. On the pairwise coprime open set, each of these pairwise resultants functions as a regular unit. Because we are missing k-1 scaling dimensions, we must introduce k-1 normalising functions, denoted as g, to restore the balance and complete the system. Applying the Cauchy-Binet formula to these normalizing functions allows us to expand the determinant. This brings us to the second half of the factorization, a distinct determinant line generated by the variables of the missing scaling torus. Classical methods already established that monic polynomial multiplication Jacobians equal Sylvester resultants. The contribution here is the specific explicit integral non-monic affine tensor and its orientation. The differential geometry successfully factors the determinant line and isolates the missing scaling torus. However, the underlying arithmetic structure controlling that torus remains entirely undefined at this stage. To lock down that arithmetic structure, the normalizing functions must act as semi-invariants. This chart shows the resulting integer character matrix, W. The candidate calculates the global Smith normal form of this matrix, yielding a diagonal matrix of G through G times H of E. In the two-factor parent theorem, W was simply a 1-by-1 matrix with a single degree difference. Here, it expands into a complete edge character matrix capable of handling multi-factor relationships. The diagonal variables are strictly defined. G is the greatest common divisor of the polynomial degrees, and H of E is the top determinantal divisor of the primitive complete edge character matrix. Focusing on the H of E component reveals the strongest arithmetic assertion. The primitive co-kernel is cyclic, presenting this exact one-generator local presentation over the p local integers. This local presentation over z sub p dictates the exact p-adic valuation of the top divisor, defining precisely which primes can occur. It also specifically recovers the correct parity rule when evaluating the prime p equals 2. Through these precise local valuations, the calculation provides full bad characteristic support for the entire geometric system. By applying Cartier duality to this lattice co-kernel, we identify the canonical residual group scheme. These same arithmetic constraints can be computed strictly from spanning tree minors, rather than the full matrix. This spanning tree equivalence bridges the result directly to signed incidence and arithmetic matrid methods, while maintaining the specific cross-weighted quotient required for this factorization problem. Calculating these exact Smith invariants mathematically locks down the residual finite diagonalizable group. The abstract geometric ambiguity of the lost scaling directions is now represented by precise integer arithmetic. We translate this arithmetic matrix into the topological space of the normalized charts. On the square-free locus, the projective factorization space acts as a finite adel cover of the coefficient space. A point in this space is defined as a labeled partition of B distinct roots into blocks, corresponding to the specified sizes of the original factors. This formula calculates the generic covering degree for the unnormalized space. When we apply the integer character matrix W, it multiplies the covering degree by the absolute value of the determinant of W. The geometric consequence of this multiplication is the addition of a torus isogeny via a square character normalization. Achieving this proven finite locally free degree requires generic shrinking of the space to ensure differential conditions hold globally. Notice how the formula behaves in positive characteristic environments. The Smith invariant factors of W split this covering degree into distinct separable and inseparable branches. The invariant factors directly dictate the distribution of the degree between the separable geometry and the inseparable characteristic-dependent behavior. By combining these layers, the topological space of the normalized charts perfectly marries the classical root partition geometry with the integer arithmetic of the torus isogeny degree. This schematic illustrates the full vertical stack of the factorization model. The pairwise resultants calculate the differential rank loss, the character matrices define the integer arithmetic of the scaling torus, and the root partitions map the global normalized geometry. However, a rigorous mathematical release must define its own boundaries, and there is a strict separation between local and global conditions here. Having a constant Jacobian serves only as a local differential condition. This determinant-like identity does not automatically produce a Keller map on affine space. For a Keller map to exist, a factorization slice must additionally be an actual affine space and exhibit the required global non-proper or multiple fiber behavior. That affine slice recognition problem remains the central, unresolved geometric bottleneck in this field. Furthermore, the epistemic status of this candidate paper is strictly defined. It is an anonymous, unrefereed release. Its assurance rests entirely on internal deterministic replay rather than external peer review. The package's computational audit logs 129,352 positive checks using exact SymPy and Flint backends, and 18 deliberate negative controls successfully detected. The highest value next steps for researchers involved formalizing the local Smith presentation in a proof assistant and classifying all regular unit and polynomial normalizers on the pairwise coprime locus. Separating the exact algebraic verification of the local determinant line from the unresolved global Keller map problem provides a rigorous, bounded foundation for elimination theorists moving forward.